Welcome back, everyone. This is mini lecture number 3 for CS-163 at the University of Wisconsin-Eau Claire. I'm Jess Vriesma, and I will be talking about recursive functions. This is covered a little bit in section 5.10 of our textbook, and the triangle shown here on the right is the Sierpinski triangle, and I challenge you by the end of this lecture to be able to describe how is that triangle an example of something that is recursive. Jot it down in your notes and come back here when you're done with this. Before we get started, I want to make sure that you understand these things. How do you pass parameters to a function in C++? How do you get the return value from a function? And how do you call a function in C++? Basically, how do you use basic functions in C++? If you're not quite sure, make sure that you get this and make sure that you can understand it from one of the previous lectures before moving on in this lecture. Recursion occurs when a thing is defined in terms of itself or of its type. So this picture shown here is recursive because it shows a girl holding a picture of herself holding a picture, 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 and I could go on and on. So this is an example of recursion. And actually, this is an example of something called the Droste effect, when a picture appears recursively within itself. So if you ever see something like that visually, that's the Droste effect. But how does that feature in computer programming? Another way of defining recursion is saying that recursion is the process of applying a given procedure to itself. A recursive function, in either computer science or mathematics, is a function that is defined in terms of itself. That is, it calls itself. So in math, you can't calculate the value of a recursive function unless you know another value of that recursive function. Or in computer science, if you have a recursive function, it's a function that will call itself. So somewhere in the definition of a function, it will call, well, it'll call itself. And you'll see an example of that in a couple slides. Now there are two very similar but different terms, recursion and iteration. So let's start with definitions and see how they're different, and then let's see how they maybe are similar. Recursion, we said, was the process of applying a given procedure to itself over and over again. Iteration is the process of applying a given procedure several times to the same problem. So in recursion, I might use recursion to break down a problem and solve a smaller piece of it, maybe zoom in on something. Iteration, instead of trying to zoom in or break a problem down, I'm going to look at the same problem and just apply the same steps that I applied before over and over and over again to it. In computer science, recursion happens when a function calls itself, or when a function is defined in terms of itself. Same thing. This often happens when we split a problem up into smaller pieces, like for instance the factorial. We say that the factorial of n is equal to n times n minus 1 times n minus 2 times n minus 3, and so on until we're multiplying by 3 times 2 times 1. We can also say that the factorial of n is equal to n times the factorial of n minus 1. And then the factorial of n minus 1 is equal to the factorial of n, or is equal to n minus 1 times the factorial of n minus 2, and so on and so on and so on. So in that case, you're splitting up a problem into smaller pieces and solving each one. Iteration usually happens in for loops, do loops, or while loops. And it's just doing the same set of same steps over and over again to data. So this often happens when we do the same procedure to the same data. I'm a step ahead of myself there. So an example of recursion might be you dig a hole in your backyard, and then you dig a small hole at the bottom of your hole. And then you dig a smaller hole at the bottom of your small hole. And then you dig an even smaller hole at the bottom of your smaller hole, and so on and so on. Each time you're digging a smaller hole at the bottom of the hole that you had before. Iteration, an example of that would be you dig a hole in your backyard, so same starting place, but now instead of saying you dig a smaller hole at the bottom of your little hole and then digging a smaller hole at the bottom of that, and each time you get a smaller hole, here you just dig the hole a little deeper. Dig a foot deeper, dig a foot deeper, dig a foot deeper, dig a foot deeper, dig a foot deeper. and so on and so on. So they're similar, but they're a little bit different. Now, in both iteration and recursion, it's really important to have an end condition. I'm going to stop talking about iteration for now, and I'm going to focus more on recursion for the rest of this lecture. So, infinite recursion is what happens when recursion happens without an end condition. It means that you're recursing infinitely without end. So here we have an example of that. This is the Fibonacci sequence, which you may have seen before. So in the Fibonacci sequence, you start with the number 0 and the number 1. Those are the first two numbers in your sequence. So Fibonacci 1 is 0, Fibonacci 2 is 1. And then the next number in the sequence is equal to the sum of the two numbers before it. So Fibonacci sequence number 3 would be 0 plus 1, so 1. Fibonacci 4 would be 1 plus 1 is 2. Fibonacci 5 would be 1 plus 2 is 3. And then 2 plus 3 is 5. And then 3 plus 5 is 8. 5 plus 8 is, can't do math right now, 13. You get the idea. You keep going, going, going. So this is an example of a recursive function in mathematics. And if we wanted to code this up on a computer, sure enough, it would also be an example of a recursive algorithm in C++ as well. So here's the function that I've written so far. It's not quite right because it doesn't have an end condition. So what this does is it's all using unsigned values because we don't need to worry about negative numbers here. The Fibonacci function will take an integer n, which will correspond to f of 1 of above, the 1 would be n. F of 2 equals 1, the 2 would be n. So here I'm going to calculate the number, the sum of the two previous Fibonacci numbers. So just like in the second line of the comment at the top of this function header, I have f of n equals f of n minus 1 plus f of n minus 2. The first row line of code in my function Fibonacci here says calculate the value, current val, as the sum of the two previous Fibonacci numbers. So calculate the value of Fibonacci at n minus 1 plus the value of Fibonacci at n minus 2. Then output the value and the index, the number n, and return this value. So let's see what this would be like. Let's say that I want to calculate what the fourth Fibonacci number is. To do that, I'm going to have to calculate what the third Fibonacci number is and the second number. And I'm going to have to add Fibonacci 2 plus Fibonacci 3. That will give me Fibonacci 4. So I have to calculate Fibonacci 3 and Fibonacci 2. In my function, it will call Fibonacci with n equals 3, and then it will say plus Fibonacci n minus 2. So 4 minus 2 is 2. So it'll call Fibonacci 3 and it will call Fibonacci 2. It will sum those together and it will say that's what Fibonacci 4 is equal to. So what are Fibonacci 3 and 2? Fibonacci 3 is going to be equal to Fibonacci 3 minus 1 plus Fibonacci 3 minus 2. So Fibonacci 2 plus Fibonacci 1. So now we need to calculate what Fibonacci 2 is, and then later Fibonacci 1. So Fibonacci 2 is going to be equal, according to the recursive formula, to Fibonacci 2 minus 1 plus Fibonacci 2 minus 2. So Fibonacci 2 is equal to Fibonacci 1 plus Fibonacci 0. Okay, we can do that. Fibonacci 1 and Fibonacci 0. Fibonacci 1 is going to be equal to Fibonacci 1 minus 1 plus Fibonacci 1 minus 2. So Fibonacci 1 is going to be equal to Fibonacci 0 plus Fibonacci negative 1. I imagine that you're starting to see what the problem is with this approach. Nowhere in our Fibonacci sequence function have we ever said to do anything other than just call the same function. So as soon as we call the Fibonacci program or function the first time, it's going to call itself, and it's going to call itself, and it's going to keep calling itself twice every time. And there's no stop. What we need are end conditions in our Fibonacci function. Every recursive function needs to have some kind of end function, because otherwise it's just going to keep calling itself forever until the computer kills the program, because the computer is fed up with your function. So how do we do that? Well, in the case of the Fibonacci sequence, we know the two starting values. We know Fibonacci 1 is equal to 0, and Fibonacci with n equals 2 is equal to 1. Fibonacci 1 is 0, Fibonacci 2 is 1. From those two starting points, we can calculate all of the rest of the Fibonacci sequence. Those are our end conditions. If we ever hit Fibonacci with n equals 2, or Fibonacci with n equals 1, we can stop and just return the value that we know that those functions have. We don't have to try to calculate them recursively. So here's an example of the fixed version of the Fibonacci function. What I've added here are a number of if-else statements that check the value of n to see what value it is. Now, we could have n equals 0. Another user might say, okay, I'm going to say Fibonacci n equals 0. What's the result? Now, the Fibonacci sequence is really only defined for counting numbers starting from 1. So n equals 1, n equals 2, n equals 3, and so on. With n equals 0 is technically undefined as we're setting it up. So we're just going to give an error and exit. We could also just return 0 if we wanted to. In this case, you could say that the Fibonacci of n equals 0 is defined to be 0. We're not going to go there right now. So if n is not equal to 0, else if n equals 1, so if we call Fibonacci n equals 1, we know that that has to be 0 from the comment at the top of this function. F of 1 is 0. So return 0. But if n is not equal to 1, maybe n is equal to 2. So else if n equals 2, return 1. That's because the second number in the Fibonacci sequence is 1. So those are our two end conditions. If n equals 1, return 0. If n equals 2, return 1. If n is not equal to 0, 1, or 2, else return Fibonacci n minus 1 plus Fibonacci n minus 2. And there we have the same thing we had before, where we have a recursive function. Now the function is calling itself. But now, because it has those end conditions, it won't recurse forever. It does have a finite stopping point. And let's see if we can trace that now. So say we call Fibonacci sequence with n equals 4, like we did before. Now shown here below in this gray box is the same Fibonacci function from the previous page, but I've taken out the part where we check whether or not n is equal to 0. I'm going to assume that nobody calls this function with n equals 0. And if that assumption is true, then this version of the Fibonacci function is the same as the one on the previous slide. It's shorter and it fits in the slide better. So Fibonacci 4. 4 is not equal to 1, 4 is not equal to 2, else return Fibonacci 4 minus 1 plus Fibonacci 4 minus 2. So that's going to call Fibonacci with n equals 3, and then it's going to call Fibonacci with n equals 2. Fibonacci 4 is equal to Fibonacci 3 plus Fibonacci 2. So now I need to calculate Fibonacci 3 and I need to calculate Fibonacci 2. Let's do 3 first, because it's first in order. So Fibonacci with n equals 3, well, n is not 1, n is not 2, else return Fibonacci 3 minus 1 plus Fibonacci 3 minus 2. That's going to be Fibonacci 2 plus Fibonacci 1. Now I need to calculate Fibonacci 2 and 1. Fibonacci 2, let's do that first because it's first in order. Fibonacci with n equals 2. Is n equal 1? Nope. Is 2 equal 2? Yes. So return 1. So here we know that Fibonacci 2 equals 1. So we're not going to keep calling Fibonacci, the Fibonacci function. We're going to stop there. But we still need to calculate Fibonacci 1 in order to calculate Fibonacci 3, in order to calculate Fibonacci 4. So Fibonacci 1 is going to be equal, well, let's trace it. If we call Fibonacci with n equals 1, the first line of code is if n equals 1, return 0. Yay! We now know that Fibonacci 1 equals 0, so we return it. Then we can try to figure out what Fibonacci 3 is. We said before that Fibonacci 3 is equal to Fibonacci 2 plus Fibonacci 1. So 1 plus 0, or 1. Now we've calculated what Fibonacci 3 is. Now we still need Fibonacci 2 to be able to calculate Fibonacci 4. We have Fibonacci 3, we need Fibonacci 2 to calculate Fibonacci 4. So let's do it with n equals 2. We know that we'll get 1. So that equals 1. Now I have Fibonacci 3 and I have Fibonacci 2. I can add those together to get Fibonacci 4. So, in summary, what is recursion? What is iteration? I want you to be able to give answers for those. So please pause this video here, go through these 6 questions, and write down an answer to them. Then maybe go back, if you're not sure about 1 or 2, go back to this through this video and see if you got them right, or see if you can give a better answer to them. If you're not sure with any of them and you think you'd like some help, let me know. I'd love to help. I would also like to give you this practice problem. In this problem, I want you to write a function to calculate the factorial of a number n. Now here I'm going to assume that n is an unsigned long int. Now if you remember what an unsigned long int is, unsigned means that it's going to be positive, not negative, and a long int means that it's going to have a lot more ones and zeros. It's going to be more bytes of memory than a regular unsigned int. Twice as many, in fact. So this is going to be able to store bigger numbers. And why do I want to do that? Well, the Fibonacci sequence, or sorry, not the Fibonacci sequence, the factorial numbers get really big really fast. So if you do like the factorial of 100, it's huge. If you do the factorial of 20, it's also really, really big. So even with small values of n, you're going to get big results. So the way that factorial is defined is n factorial, where n is a positive integer, is equal to n times n minus 1 times n minus 2 times n minus 3 and so on until you hit 1. So if I have 5 factorial, that will equal 5 times 4 times 3 times 2 times 1. 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. So 5 factorial is 120. If you want to see what all the other numbers in this sequence could be, you can go ahead and, or if you want more information, check out the Wikipedia page here. So what I want you to do is I want you to write this function, but I also want you to write a main method to test your function. Call factorial with 1, call factorial with n equals 2, call factorial with n equals 3, and do that for maybe 5, 6, 7, 8 of them, and see if your factorial function gives the same results as what are tabulated on that Wikipedia page. Now, if you can do that, awesome. More power to you. Way to go. I high five you. If you try that and you can't get it, now again, pause here because I'm about to give some hints. I want you to try it first. Really, this will help you. If you can't get it, here are some hints in 3, 2, 1. The first hint is that the algorithm for calculating a factorial function is recursive. So n factorial equals n times n minus 1 factorial. So if n equals 5, this is saying that 5 factorial equals 5 times 4 factorial. Does that work? Yeah. 5 times 4 times 3 times 2 times 1, which is 5 factorial, equals 5 times 4 factorial, which is 4 times 3 times 2 times 1. So yeah, 5 times 4 times 3 times 2 times 1 equals 5 times 4 times 3 times 2 times 1. So you can write it as a recursive function. Second clue is that the factorial of 0 and 1 are both defined to be 1, and you can use this as an end condition for your factorial function. So if you go into your function, you can say, well, if n equals 1 or if n equals 0, then return 1. The final hint is that, and it's not really so much of a hint as more of a be careful. Factorial function grows really fast. And so even with modest values of n, like maybe n of, I haven't actually done it myself in terms of seeing where the limit is, but maybe n of say 20 or 30, that number can be big enough that it will hit near the limit of how big an unsigned integer can get. And if that's the case, you'll get an overflow error, and it will be a silent error. It won't tell you that this is an error unless you compile your code a certain way. So it'll just, factorial of, say, 15 will be big. Factorial of 16 will be bigger. Factorial of 17 will be even bigger. Then factorial of 18 will be tiny. Just those numbers, for example. And if something like that happens, that means that you've probably hit the top of how big a number can be stored in an unsigned long int. If that's the case, you could always use an unsigned long int if you want. But then there's a limit to that as well. So it only works up to a point. I hope that you guys have had fun listening to this. I've had fun making it, and I hope that you guys have a great rest of your day. If you have any questions with anything, as always, please let me know. Take care, stay classy, and I'll see you guys later. Bye-bye.